Let me know if you can hear me, like if my voice is audible. Please drop it in the live chat. Uh, can you please? Yep. Thanks, Ashank. Yep. Thanks, Subhash. So I'll start off. So this today I'm going to be speaking about introduction to primes, like how do you compute them, how do you check if a number is prime, and some facts and properties about primes, and also divisors. This is going to be the start of the number theory section that I discussed in my introduction. All right. Yeah. Thanks for letting me know that I'm audible. Yeah. So a little about myself. I'm Sai Avinash, and I'm an SRE SWE at Google Dublin. I'm currently working there. I'm All India Rank 3 at CodeChef, intern at Uber. I previously interned there. I'm a master at Code Forces, and I'm a Snagdon finalist. The subjects that I take are maths, dynamic programming, graphs, and a lot of other computer programming topics. So don't forget to use the code SciLive to get 10% off on the Unacademy Plus subscription. So what do you get with the Plus subscription? Like, what are the benefits? You get to interact with India's best programmers. There are going to be live interactive classes, like you can interact with the best programmers live. And there is going to be complete doubt support. Like, you can get to ask your doubts live to India's best programmers. And to top it all off, you're going to, you can ask your practice problems, like you can solve them, and you can ask your doubts in the doubt support section. So use the code SciLive to get a 10% off on the Unacademy Plus subscription. So there are new batches coming up on Unacademy. They're exciting. So starting with Transpire, it's an OS DBMS and networking master course, the core CS fundamentals. And it goes live on 20th July. It's a 1-month durated course. There's Ekalavya 3.0, which is a complete course on Java programming for beginners. It's an 8-month durated course. It goes live on 21st July. Then there's Brahmahastra 3.0. It's an exclusive 5-month learning track for college and off-campus placements. It's a 5-month durated course that goes live on 20th July. Then there's Mahayodha 2.0, the 6-week master course on advanced programming topics. It goes live on 20th July. There's Bug Bounty as well. Like, it's an opportunity for all learners to report any inappropriate content in the video. Be the first one to report a particular issue to claim your prize. And do report any inappropriate content using the form in the description. It's going to be helpful for all the learners out there. Like, it's good to have like appropriate content in the platform. So if you think this is going to be useful to you, and I really think it will if you're like starting up with programming, do like, share, and subscribe. So just drink some water. So, introduction to primes. What are they? So primes are primes can be seen as indivisible natural numbers. Natural numbers that can't be divided anymore. I mean, one is an exception, but all other natural numbers that can't be divided anymore. Like, they're the atomic natural numbers. You can relate them to actual atoms in, say, chemistry or something. For example, H2O is water, and 12 is 2 square into 3. And I mean, in chemistry, maybe the order matters or something like that, but you get the idea. Like, all natural numbers can be uniquely represented as the product of powers of their respective primes. Like 210 can be written as 2 into 3 into 5 into 7, and so on. Like, yeah. So that is, so primes are numbers that don't have any factors other than 1 and itself. Like 3 is a prime, 2 is a prime, 37 is a prime, 42 isn't, because 42 is divisible into 2 into 41. 2 into 21. I guess you all know that already. Cool. So let's discuss one property of, like, let's discuss the property of a natural number. Like, a natural number can be uniquely represented as a product of its primes. For example, 69 is represented as 3 into 23. 420 is represented as 2 into 2 square into 3 into 5 into 7. 100 is represented as 2 square into 5 square. There is no other way you can represent it 100 or 420 as a product of its primes. It might be a bit obvious to you. Now, next, how many primes are there? Well, how many primes are there? Are there 100 primes overall in the universe, like in all the natural numbers combined? How many primes are there? Are there 1,000? Or are there less than 1,000? No, turns out there are infinitely many prime numbers. Infinitely many. Like, there are going to be infinitely many. You want to discuss we can discuss the proof also. So let's prove by contradiction. So say there are only finite number of prime numbers. Let's call them P1, P2, P3, so on till Pk. Finite number, there are only k prime numbers. Like, let's say there are only k prime numbers, P1, P2, P3. Now look at this number, P1 into P2 into P3 into so on till Pk plus 1, add 1 to that. This number, this new number n, it's not divisible by any of them because it gives it is not divisible by P1 because P1 into something plus 1, not divisible by P1. It's not divisible by P2 either, not divisible by any of the prime numbers. And it's bigger than all of the prime numbers, which means that n has to be a new prime number. So we have discovered the k plus 1 prime number if we assume that there are only k prime numbers, which is a contradiction. Therefore, you can't find a k, which means the number of prime numbers are they're not finite, they're infinite. That's it. Good. Now, how do we check? How do you check if a number is prime? How do you check, like without a program? How do you check? So, if you're given a number 20, how do you check? You start from 2. You see 2 is divisible by 20 is divisible by 2. So, like, what did we discuss prime numbers? The only factors of a prime number are 1 and itself. All right? It has only two factors. Every prime number has only 2 factors, 1 and itself, exactly 2. But we found that 2 is a factor of 20 and we discarded 20 as saying that it's not a prime. Cool. We look at 13, for example. Well, we look at 13. Now, how do we check if we want to tell if it's a prime or not? So we start at 2. Then we say 13 is not divisible by 2. Then we go to 3, not 4, not divisible, 5, not divisible, 6, not divisible, 7, and so on till 11 and 12, sorry, till n minus 1. So we iterate from 2 to 12 and we check if 13 is divisible by any of these, and turns out it is not divisible by any of these numbers. So we tell that 13 is a prime number. If it is divisible by any of these numbers, then 13 is not a prime number. Got it? Yeah. It's as simple as that. Now, how do we write this in code? How do we check a number? How do we check if a number is prime? It's fairly straightforward. So, let's call a function bool is prime int n. Note that 1 is not a prime. So, if n equals 1, return false. Now, for int I equals 2, I less than equal to n minus 2, I plus plus, if n modulo I equals 0, which means if I is a factor of n, return false. If it's not a factor, if no two from 2 to n minus 2, if none of the numbers are factors, then you return true. That's simple. That's simple. Like you don't. I mean, this is just checking a number if a number is prime. Now, what is the complexity of this? The complexity. Look, if a number is prime, like say number is 23, we're going from 2 to 23. 2 to 20, actually this is n minus 1, so my bad. If a number is prime, say we take 23, we go from 2 to 22 and we check each and every number. That means we're checking n minus 2 numbers if n is prime. And you're not, and it's gonna fail this test every time. Like it's gonna, like you say 2 is not a factor of 23. So again, we check 3 is not a factor of 23 again. So it's gonna happen about O of n times. So the complexity of this is going to be O of n. Very simple. But turns out we can do faster. Like this is going to be a bit slow. So how do we get lazy about this? Like how do we skip some operations? Like the computer is going to get too tired by looking at this. So we want to get a little more faster. How do we get faster? So do we really have to check all numbers from 2 to n minus 1? Do we? No, we don't. We don't need to check all numbers. Turns out it's only sufficient if you check from 2 to root of n, and that's it. Why? Because if a number has a factor greater than root n, it will well. If a number has a factor greater than root n, it will always have a factor less than equal to root n. Less than root n. Well, I mean, if it has greater than equal to root n, it will have factor less than equal to root n as well. Take an example. 20. 1 like 2 is a factor. 2 is a factor. 10 is a factor. 4 is a factor. 5 is a factor. Every number less than root of 20 has a corresponding number greater than 20, and the other way. Like because why? Because if a is a factor, then n by a is also a factor. So if a is greater than root of n, then n by a will be less than root of n. And if a is less than root of n, n by a is going to be greater than root of n. So you don't really have to check the numbers greater than root n. Checking numbers till root n is always sufficient. That is, for example, if you want to check 23, it's enough to check till 5. 2 is not divisible by 23. 3 is not divisible by 23. 4 isn't. 5 isn't. So we say that 20 is a prime. 23 is a prime. All right. And let's take another number. 35. 35. We see 2 isn't a factor of 35. 3 isn't a factor of 35. 4 isn't. 5 is. Like, and the square root of 35 is some 5.9 or something. And that's enough. Checking till 6 is sufficient because we don't have to check after 6. If we don't have to go to 7. Like if we had to go to 7, it means that we already encountered a number less than 6 already, which is a factor of 35. So we don't need to go above 6. So we can optimize the code very quickly. Like it needs minimal modification. So we can just iterate till L equals square root of n. And we can just iterate till that. L. And this is sufficient because if a number greater than L is a factor of n, then we would have already broken early. Like it means that a number less than L is also a factor of n, as how we discussed right now. So we don't need it. So this is how we check it quickly. All right. Let's move to Sieve. One sec. Yeah. So, what's Sieve like? It's a method developed by Eratosthenes. It's also called Sieve of Eratosthenes. It's kind of hard to pronounce, but yeah. Let's discuss what it is. So, it is a method, say from 1 to n, you want to find what are the primes from 1 to n very quickly. How do we do it? How do we do it? So one way is to check each number. We call its prime function. If it's prime of I, for each I, equals 1 to n, if is prime I, then mark, we can just, well, this is a bit annoying. One sec. We can just, I'll just show it to you by code as well. For each I, mark prime of I equals 1 if the is prime of I. If that returns true, we mark it as 1, otherwise we mark it as 0. But what would be the complexity of this? So for each I, the complexity of checking a number is, if it's prime or not, is root I, as we discussed. Right. So we're doing it from I equals 1 to n. So the complexity would be n root n. O of n root n. We can do it a bit faster. No problem. We can do it a bit faster by using a method called Sieve. Like, first let's just code out this method. Bool prime primes for int I equals 1, I less than equal to I less than max n, I plus plus, prime of I equals is prime of I, is prime of I. So we call this function n times, max n times, we can just like name it max n, okay, max n. And this, each time it's going to take about root of max n operations. So the total would be O of n root n. Or you can write O of, I'll just write it in the comments, O of max n root max n. All right, cool. How do we do it quickly? Let's discuss that. Now, let's consider an array of size n. We want to compute, like first let's discuss our goal here first. This is a Boolean array of size n, like let's say n plus 1 for now. Boolean array. The first one represents 0, 1, I mean 0 doesn't make any sense, 2, 3, so on. For every number that is prime, we need to mark it as 0. Or like we can mark it as 1, you need to mark it as 1, like anything, it's up to you. 3 as 1, 4 as 0, 5 as 1, 6 as 0, 7 as 1, 8 as 0, 9 as 0, and so on. For every prime number, there should be a 1. For every non-prime number, there should be a 0. That is our goal. How do we achieve this? Like, one way, as we discussed, would be, as we discussed it here, as we did it here, for each number, call the prime function. Is prime number. Is this a prime number? And fill it into prime of I. It's as simple as that. Yeah. How do we do it quickly? We can use the Sieve method. So the Sieve method says that, like, for each I, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on. Initially mark all of them as 1. Then, starting from 2, we mark all of its multiples, like non-trivial multiples, like 4, 6, 8, 10, and so on as 0. We mark this as 0. And we mark 6 as 0, 8 as 0, 10 as 0. Then we move and so on. And then we go to 3. We mark multiples of 3 other than 3 as 0. 6 as 0. 6 is already marked 0, so it isn't required. 9 as 0, 12 as 0, so on. And we do this for all. We don't need to do it for all numbers, like we don't need to do it for 4 because we do it for all numbers which are 0. Like all numbers which are initially 1. And now we mark all its multiples except that as 0. Now, after doing it for all such numbers, in the end, the numbers which have 1 on top are going to be prime. And we are, did I forget to tell that? Like initially you need to mark 1 as 0. Yeah. We just show it by simple example, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So we mark 1 as prime. We mark 1, 0 here. That's our first step. Then we go to 2. We mark all multiples of 2 other than 2 as 0. Then we go to 3. We mark all multiples of 3 other than 3 as 0. 6 is already marked. 6 is already marked. 9, 12 is also already marked. Then we go to 5. We don't have to do it for 4 because every multiple of 4 is also a multiple of 2. So it's going to be a waste of computations, inefficient. We don't have to do that. We go to 5. We mark all multiples of 5. That's already been marked because already been marked by 2. And similarly 7, they have no multiple of 7. So look at the numbers that are left. 2, 3, 5, 7, 11. All of these are prime numbers. Great, right? So after doing this operation, after doing these operations, the numbers that are going to be unmarked are your prime numbers. Now you might think, like after each number, for each number you're marking it like you're marking all its multiples, so that's O of n for each number, and we're doing this for nearly n numbers. So isn't it quadratic? Like isn't it suboptimal? No, it isn't. Like if you write down the computation, turns out you'll get it as n log n. I'll show it to you how. So for 2, how many numbers are we marking? Since we're marking all numbers at a multiple of 2 up to n. So how many multiples of 2 are there up to n? N by 2. How many multiples of 3 up to n? N by 3. Well, it's n by 2 minus 1 other than 2, but we ignore the 1, like it's insignificant. How many multiples of 5? Note that we're marking the multiples only for prime numbers. We don't have to do it for 4 because we already did it for 2. Right? Like doing it for 4 is redundant because every number which is going to be marked by 4 was already going to be marked by 2. So 5, n by 5. So 1 is n by 2. For 2 it's n by 2. 3 is n by 3. 5 is n by 5. Plus so on. So until n by largest prime number less than or equal to n. Let's call it something. I don't know. It's very insignificant. Good. So what is this going to be? We know that this is less than n by 1 plus n by 2 plus n by 3. I'll tell you why I'm doing this. Like it might seem out of nowhere, but you'll understand why I'm doing this. This is less than this plus n by 2, n by 4 plus n by 5. So because we're just adding a few terms here, like we're adding n by 1, we're adding n by 4, n by 6, all n by composites here. Now this, I'll show you how it's less than n log n. Log n to the base 2 precisely. This is going to be less than n log n. It might seem n square at first. That's okay. Like at first glance, I thought it was n squared, but then it's actually n log n. I'll show you how. So if you look at n by 1 plus n by 2, I need to write more terms for it to be more clear, so bear with me. N by 4 plus n by 5 plus n by 6 plus n by 7 plus so on. This is again less than n by 1 plus n by 2 plus n by 2 plus n by 4 plus n by 4 plus n by 4 plus n by 4, so on. So I'm writing this as this, these two as this. Again, I'll tell you why. You'll understand why it'll all fall into place later. So n by 3 is less than n by 2, so on. N by 5 is less than n by 4, n by 6 is less than n by 4, n by 7 is less than n by 4, and so on. We write it till the end. So this is going to be less than or equal to this. Look at what this is. This is basically n plus this amounts to n and 1 by 2 plus 1 by 2. So we write it as powers of 2, like 4 powers of 2 square, 8 powers of 2 cube, so on. And this is also going to be n. So for 2 power 0 we have n, for 2 power 1 we have n, 2 square we have n. Till where can you go? It's to so on till n by n, right? And this kind of, these circles are going to be drawn only log n to the base 2 times. Like we are doubling the denominator. Like till 7 we're going to 2 square. Till 16, like 8, 9, 10, 11, all of them we're going to write as n by 8. So this whole sum is going to be log n to the base 2, less than or equal to log n to the base 2. So if you look at it closely, this is less than or equal to this, and this is nearly log n to the base 2. So using this logic, we get n by 2 plus n by 3 plus n by 5 plus so on is less than or equal to n by 1 plus n by 2 plus n by 3, so on. This we know that is less than or equal to log n, n log n, which means this is less than n log n. This is how sieve of ferrocerines is O of n log n. Some, like, there are some optimizations which you can make it as n of log n. We'll discuss that. Great. Like, as we discussed, like initially this might look n into n, like we're doing n by 2, n by 3. All of them are O of n. You're adding all of O of n. And why is it not n square? We just discussed why it isn't. So it's O of n log n. Great. So let's go ahead and start coding it then. This is no longer needed. We have a more optimal method here. I mean, that might be required for bigger numbers, but for the number that we are trying, it's not required. So what did we discuss? We discussed first we're going to mark all numbers in the array as 1. Prime of I equals 1. True. All primes are true. Then we mark 1 isn't a prime. False. Now we start from 2. I equals 2. We start from I equals 2. We go from I less than max n, I plus plus. Hey, please let me know if there's any doubt in between. I'm just looking at the chat once in a while. So, answer. So if I is a prime number, one sec, just adjusting my camera a bit. No problem. Yeah. If I is a prime number, we mark all its multiples. J equals 2 into I. All its multiples other than I. Like, we don't want to mark I as not prime again. If I is prime, we don't want to mark it not prime again. Like, that's, yeah, this is stupid. Max n, J plus equals I. If you look at this closely, we are iterating through all multiples of prime numbers. If I is 2, I is going to be prime initially. We mark all its multiples as false. Like all multiples of 2 other than 2 aren't going to be prime. That's what we are doing here. All multiples of 3 other than 3 are not going to be prime. That's what we're doing here again. All right. Cool. Now, in the end, the array that you get here, prime, whatever the output that you get, all of these numbers, it's going to be prime of I equals 1 if in the end, like after you do all this part, all this, you're going to prime of I equals 1 only if I is prime. Okay, Sumitava is asking directly, this is not used in questions, how to understand when to use which prime method. All right, so Sumitava, okay, I'll just complete this and I'll tell you what that is. Okay, like I'll answer your question. So after completing this whole thing, prime of I will be equal to 1 if I is prime. Prime of I will be equal to 0 if I isn't a prime. Another mathematical way to write this is prime of I equals 1 if and only if I is prime. I mean, I'm just writing that so that like it might be useful later. I don't know. So, all right. So this method is n log n. Like it's less than n log n. It's definitely less than n log n, but n log n is like usually sufficient. Okay. There's another optimization on top of this. I'll explain that. Like after answering Sumitava's question here. All right. So, what do we know? Like, which prime method should we use? So, sometimes if you want to check if n is a prime, and if n is up to 10 power, n is say 10 power 12, or 10 is up to 10 power 12, we cannot use Sieve because Sieve computes 1 to n, all of them in n log n. Yes, I'll get to that. Like I'll get that. The initial optimization was just for explaining. I'll do that optimization. I'll show it to you. Okay, back to Sumita's question. N is less than 10 power 12. If n is about 10 power 12, we can't do the Sieve method because it's going to do n log n. It's going to take n log n. And n log n is 10 power 12 into log of 10 to the power 12. We know that our computers like can do about 10 to the power 8 operations in a single second. And 10 to the power 12 is going to take a day. Half a day or so. So whatever this is, like, so if n is up to 10 power 12 and if you want to check if it's a prime, then we use the square root n method. What is square root of n? If you want to check if a single number is prime, it's probably useful to do the square root of n method, like use its prime, iterating from 1 to root n. But if you want to check if all numbers from 1 to n are prime, then we can use the Sieve method because it's doing some magic and telling you if all numbers are prime or not in one go. Whereas if you want to check if a single number is prime, don't do the Sieve method. It's simply useless. You can directly use the square root n method. Hope I answered that question. Let me know if there's any doubts. And coming back to Yash, yes, J starts from I into I. There's no harm if you start from 2 into I. It's going to be a little slow, but it's like insignificant. And yes, we can start from I into I. Why? J equals I into I. If J equals I into I, what happens? We don't need to iterate from 2 into I. But meaning, like, say you're marking multiples of 7. You don't have to start from 14. You don't have to mark 14 as 14 as not prime, 21 as not prime, 35 as not, what is this? 28 is not prime, and so on. You can directly start from 49 as not prime. Because 14 is already marked by 2 as not prime. We don't have to mark it again by 7. 21 is already not prime. We don't have to mark it by 7. Like, it is already marked by 3. Like, we are going from small to top, right? So we don't need to like go from 14 again. We want to be fast. We don't want to like go from the very bottom. Like we can directly start on 7 into 7, like I into I. I into 1, I into, sorry, one sec. I into 2, I into 3, I into 4, all of them have already been marked by 2, 3. I into 4 will also marked by 2. I into 5 was marked by 5. We can directly start from I into I instead, like being lazy. So an optimization here is I into I, less than max n. As simple as that. And one thing that you have to be careful that one thing you have to be really careful is if max n is 1e5, I into I can overflow because integer is just up to 10 power 9 or 3 into 10 to the power 9, and 1e5 is going to overflow 1e5 into 1e5. It's going to be huge. It's 10 power 10, which is greater than int, what int can afford. So what you do here is, if I into I greater than max n, return, break. Why are we doing that? It means I into I will never be greater than 1e5. So this will never be greater than 1e5. We just have to go to the root of max n. Meaning, I'll just have some auto. We just have to go to the root of max n. Because the numbers that are going to be greater than root of max n, they won't contribute anything. Like I into I, here j is already less than max n. If I into I is already greater than max n, this loop won't execute. Alright, cool. So the complexity of this is n log of log n. The proof is a bit tricky, and honestly, even I don't know it. And it's, if you can read it up to, but I honestly don't know it. The complexity of this is O of log f, n log of log n, n log. Yeah, it's a bit hard to explain as well why that is, especially because I don't know. Yeah. Any doubts? Any doubts so far? I'm looking at the comment section, the chat section. If you have any doubts, please let me know. Cool. Moving on. Divisors. What are they? What are divisors? We've studied it in high school. A is a divisor of B if divisor is more or less defined for integers, like natural numbers to be specific, but you can do it for integers in general, but natural numbers. 3 is a divisor of 12, 4 is a divisor of 16, 5 is a divisor of 10. Yep. Thanks for saying that there are no doubts. I'm moving on to divisors. So yeah, so on. Cool. So how many, what can we tell about divisors? Given a number n, how many divisors does it have? Say we have 30. We have 1 into 30, 2 into 15, 3 into 10, 5 into 6, and again 6 into 5, 10 into 3, 15 into 2, 30 into 1. There are totally 8 divisors. Cool. All right. Now, given a number n, how are the divisors going to look? How will they look? So, say a number, let's take a highly composite number not 108. It's 2 cube into 3 square. Well, 108 is 2 square into 3 cube. How many divisors does it have? One way, how are the divisors going to look? 108 is 1 into 108, 2 into 54, so on. We can keep listing it. It's going to be a bit boring, but you can keep listing it. Another way to look at the divisors. All the divisors should be of the form 2 power a into 3 to the power b, correct? Where a is less than or equal to 2 and b is less than or equal to 3. Got it? 0 less than or equal to a less than or equal to 0 less than or equal to b less than or equal to 3. And how many ways are there to do this? A can be 0, 1 or 2, b can be 0, 1, 2 or 3. So there are 3 into 4 ways. Got it? Like 108 equals 2 square into 3 cube. So 2 power 0, 2 power 1, 2 power 2. Let's take this as one set. Next. 3 to the power 0, 3 to the power 1, 3 to the power 2, 3 to the power 3. Alright, this is another set. We can take any number from this set and any number from this set and multiply, and we are going to get 108. We are going to get it as a factor of 108. And all factors, ethics could samajh nahi aa raha. Can you explain which part you're not understanding? I'll try to be more clear there. So we can take 3 numbers from here and 4 numbers from here. So that's 3 into 4 equals 12. All right. Similarly, say 108 into 7. Let's take the number 756. It's 2 square into 3 cube into 7. What are the number of factors for this? It's going to be 1, 2. Like we can take any number from 2 power 0 to 1, 2 square. Similar, very similar. 3 to the power 1, 3 to the power 3 power 0, 3 to the power 1, 3 to the power 2, and 3 to the power 3. Then we can take 7 power 0, 7 power 1. We can take any number from this set, any number from this set, any number from this set, and multiply. Let's say we take 2 power 1 and 3 square and 7 power 0. This is going to be a factor of this. This is like any number from set A, any number from set B, any number from set C. We take it and multiply, we're going to get it as a factor of 756. And how many ways are there to do that? Set A has 3 numbers, set B has 4 numbers, set C has 2 numbers. So 3 into 4 into 2, 3 into 4 into 2, 24 factors. Well, I mixed that up, 24 factors. Okay, Sumitava is asking if some number becomes 2 to the power 1000 or something for any number. Can you explain it more, Sumitava? Like, I'm not getting a question here. Guru Prasad, think why we have chosen 2 to the power 3 and 3 to the power A. 2 to the power A and 3 to the power A. So, as we discussed, we chose it because like we are dividing the number into its atomic parts, and we divided into prime powers because that's an easier way to look at the divisors. Like the divisors have the same prime numbers as the actual number. That's why if we divide the bigger number into prime factors, it's easier to look at the structure of the divisors if you understand. Is that clear? Like 108, like I just took it as an example, 108, 2 square, like 2 square into 3 cube. I just took it as an example because like it has two prime factors, and I split it because all its divisors will have, all its factors are going to have 2 power x and 3 to the power y. There's not going to be a new prime factor involved, because if a number has 2 to the power x and 3 to the power y and 7 to the power z, it is not going to be a factor of 108, right? If there is 7 in the, if 7 is the factor of some number, it's not going to be a factor of 108. Like that's why I divided into just like the prime numbers, and so like the calculating the answer becomes easier. Did you understand that? All right. We like when you're asked to calculate something related to divisors, or if you want to calculate GCD, dividing the number into its atomic parts is like really, it makes things really easier. Like dividing it, like for example, as we discussed in GCD also, right? GCD of two numbers A and B, 108 and say 256, like no, well, let's take 8 into 9, 72. Yes, Guru Prasad, the parts will be primes, yes. 108 and 72. We divide this into atomic parts. 2 cube into 2 square into 3 cube. This is 2 cube into 3 square. Well, this is bad. What is 72? 2 cube into 3 square. 108 is 2 square into 3 cube. Now GCD is look at the individual atomic part and then take them in. 2 square GCD. GCD, if you've seen my previous GCD lecture, you'll understand. Minimum of powers of each prime. 2 and 3. दोनों में छोटा क्या है? What's less? 2. 2 to the power 2 into 3 square and 3 cube. 3 square. This is your GCD. 2 square into 3 square. That's 36. 36 into 2 is 72 and 36 into 3 is 108. So dividing it into atomic parts usually makes a lot of number theory problems easier. Let me tell you. Like it makes a lot of number theory. Like divide into atomic parts and look at it. Try to look at it into like try to understand a pattern. Like similarly we saw here. Like that made counting divisors pretty easy as well. 210 is 2 into 3 into 5 into 7. Now how many factors? One way would be to go and like boring. It's going to be boring. 1, 2, 3, 4. We check each number if it's a factor of 210 or not. That's going to be boring. But once we know the prime factorization of 210, now we can directly tell how many divisors are there in that number. So let's look at the divisors. 2 power 0, 2 to the power 1. We can list it like this. 3 to the power 0, 3 to the power 1. 5 to the power 0, 5 to the power 1. 7 to the power 0, 7 to the power 1. We can take one number from here, one number from here, one number from here, one number from here and multiply it. And we're going to get a new number. And that number is going to be a factor of 210. And how many ways are there to do that? Like let's just take an example. We take 2 power 1 and 3 to the power 0 and 5 to the power 1 and 7 to the power 0. We're going to get 10. 2 into 1 into 5 into 7. Sorry, 2 into 1 into 5 into 0. 5 into 1, sorry. That's going to give you 10. And 10 is a factor of 210. And similarly, every other combination. So how many ways are there to do that? 2 into 2 into 2 into 2. 16 ways. Let's generalize it further. If a number n is equal to 2 to the power a into 3 to the power b into 5 to the power c into so on, the number of factors of n will be a plus 1 into b plus 1 into c plus 1. How did you get this? We get it like this. So we take the set method. Like you can remember this formula, but you don't really have to either. You can just remember the set method of doing it. Take the first set as 2 power 0, 2 to the power 1, so on till 2 to the power a. There are going to be a plus 1 elements here, starting from 0 to a. Take the next set, 3 to the power 0, 3 to the power 1, so on till 3 to the power b. Next set, 5 to the power 0, 5 to the power 1, so on till 5 to the power c. There are a plus 1 elements here, b plus 1 elements here, c plus 1 elements here. We can take any element from this, any element from this, and any element from this, and we can multiply that. Like we're going to multiply all that. Whatever we get here. We're going to multiply that, and that number is always going to be a factor of n, because we just saw a few examples as well. And how many ways are there to do that? A plus 1 ways to choose an element in the first set, multiplied by b plus 1, multiplied by c plus 1, and so on for other primes as well. So if given a prime factorization, you can directly do this. A plus 1 into b plus 1 into c plus 1 and so on. Got it? Yeah. This is one way to look at primes and how they relate with divisors. Now, let me just have some water. Any doubts so far? Yeah. Assuming there were 16 ways, right? And yeah, I'm from AP. Yeah. Cool. Let's look at another way to calculate primes. Now, given a number n, you want to print all its primes. Only given a number n, print all its primes. The previous method that I told, the prime factorization, that is just a way for you to look at it. It will be used in problems indirectly. Like, it's not very useful for computation or something, but like directly computing it, but it's going to be useful for problems indirectly. And I'll give you those problems in the next few lectures or so. Okay, no worries. So, given a number n, how do you print all its factors? Given 24, I want you to print 1, 2, 3, 4. Oh, it has a lot of factors actually. You want to print all its factors. It's very straightforward. Like, how would you do it? Like, if you had to do it on a pen and paper. So say 24 itself. Okay, let's just another number, 25, 28. We start from 1. I'll just adjust the camera. We start from 1. Like, if you had to do it in an exam, like 10th class mein exam tha, list out all factors of 28. I mean, not 10th, like 6 or something. All factors of 28. How would you do it? Go from 1. Then you check 2. 2 is also a factor. 3 is also a factor. 3 is not a factor. Cool. You go to 4. 4 is a factor. 5, no. 6, nope. 7, yes. 8, nope. So on. You get 14, yes. And like, you can do it. It's going to be long. No point of me writing all of it. 28. So that's it. Now, from 1 to n, from 1 to 28. Yep, Shravan, you're right. 1 to n by 2 in a loop is also sufficient. That's one optimization. Like, yeah, good one. 1 to, this is going to take n operations, like 28 times. That's going to be boring. That's going to be boring. 28 times. 28, you have to do it till 28. One optimization you might do is like, you don't have to go till 28. You can go till 14. Because 14 to 28, like 15, so on till 26, 27. None of these numbers are going to be factors of 28. So there's no need to go through them. 14 is enough. So from 28, we reduce to 14. Good job. Now, how do you do it even further? Turns out you can. So for a given number n, 28, we looked at its factors, right? 1 into 28, 2 into 14, 4 into 7. That's it. Now, look at these. Look at them. Like, just look at them for 2 seconds. Like, can you make an observation? If you know this number, we know this number already. This number gives us this number already. Like, every number has its complement. And if that number is less than root n, this number has to be greater than root n. Matlab, a into b is equal to n. If 1 is less than root n, this has to be greater than root n. Correct? Okay. Yeah, Sumita was right. I and n by n. Yep. If we have I, which is a factor of n, we have n by I, which is also a factor of n. Simple. Just think about like another, it's not a great mindless exercise, but you can think about it in terms of atomic terms as well, but that's not necessary. Yeah. So you don't need to iterate till n or n by 2 either. N by 2 is a good optimization, but we don't need to iterate till then. We can iterate till root of n, and that is sufficient. Like we'll do both the methods, and I'll show it to you. Void print factors int n for int if I is a factor of n, C out n. Now this will print all factors from 1 to n. Got it? Cool. But this is going to take O of n, which is slow and boring. We don't want it. But as Shravan said, we can just run it till n by 2. But n won't be covered till n by 2, so we just print out n in the end as well. This will print all factors. This is O of n by 2. Correct. Which is again O of n. Now, we can only iterate till, it turns out we can only iterate till root of n, and we can print all the factors. Int limit. We'll iterate till limit square root of n. Concepts. Yeah. Yeah. Now, turns out this is sufficient, but we need to print two numbers for each. So when we find I is a factor of n, we know that if I is a factor of n, then n by I is also going to be a factor of n. That's what we discussed, right? In 1 to 20, for 20, if 4 is a factor of n, then 5 is also a factor of n. 4 is a factor of n, 20 by 5, 4 is also a factor of n. 100. 5 is a factor of 100. 100 by 5, which is 20, that's also a factor of 100. Here, I and L. Now see out n by I and L. Great. Now we're printing both. All right, printing all the, this will print all the prime factors. But there's a small catch in this. Can someone tell me the fact here? Like which I missed the fact here. Like a small edge case. Can someone tell it to me in the chat? Like what I missed? Sumita, yes, square root function will take log n time. But when we add it to square root n, like square root n plus log n, square root n is a function which grows even faster than log n, right? So that's why we just assume that it's square root of n. That's it. Does anyone know what the catch is? All right, I'll tell it to you. So if n is a square number, it's a perfect square, then I will, like n is equal to 36, then 6 will be equal to 36. And that is the only exception. So we will be printing 6 twice, which is wrong. We should print it exactly once. That's what the question stated. Got it? Yeah, Sumita stated correctly. If I is not equal to n by I, only then print it. All right. Yeah, that's the only catch. All right. Now, Vijay said square root of n plus 1, but honestly, that's not required. Like, it's not required. Square root of n is sufficient. Like because we are putting an equal to sign, right? Like we are including square root of n too, so it's enough. One small catch is, this is something that you shouldn't do. Like you can do, but it's going to be suboptimal. Square root of n. This loop is going to run about square root of n times, but at each time you're doing off log n, like each time you're computing what square root of n is, and that's going to take log n. At each step, it's going to take log n. So the total complexity would be square root of n into log n. This is something you need to avoid. That's why you don't need to compute it every time, right? You just need to store it in a variable, and that's it. You don't need to compute it at every loop. So int limit. That's why we discussed that we added another variable, and then put it into that variable, and have it over. Yeah, that's it. And the complexity of this would be O of log n plus square root of n. But since square root of n grows faster, we discard log n. Square root of n is the bottleneck, and that's what we included in the complexity. Great. All right. Now, so similar to primes, any questions so far? In the chat? Yeah. So, any questions so far? I can move on to the next topic. Like it's the same topic, but different somehow. No questions? All right. So now, if you want to count the number of factors, just count factors. What do you do here? You just add a variable h equals 0. I mean, factor count, and then just wherever you're printing, just increment the variable. That's it. It's fairly straightforward. And then it's an integer. Return factor count. Simple, straightforward. All right. Yep. Thanks, Pankaj. So now, what is the complexity of this? As we discussed, it's of root n. Got it? Cool. Now, if you want to count factors for a single number, for a single number, it's going to be of root n. Now, if you want to calculate number of factors for all numbers from 1 to n, meaning all numbers from 1 to n, I need an array named count, where count of x will give me the number of factors of x. Like I need to do some magic, like some algorithm I need to, or something I need to do. I want this, okay. Count of x equals x somehow. For x equals 1 to n. How will I get it quickly? One way again would be this. Same thing we do. We do it for each number. I'll just write it as a different function because it's nice to make more functions. We'll count factors. For int I equals 1, I less than equal to n. Count of I equals count factors. Very straightforward. Nothing fancy. Very straightforward. This will count all numbers, all factors of all I from 1 to n, right? And the complexity of this is going to be 1 to n. You're doing count factors, like it's root n for each thing, so it's going to be n root n, n times root n. I mean, for the smaller numbers, it's going to be n root 1 plus 2 root 2 plus 3 root 3 plus so on. But that's going to be n root n. Like, I'll just give you a list of the complexity in case you're not clear. The complexity of this would be 1 root 1 plus 2 root 2 plus 3 root 3, so on. Sorry. It's going to be root 1 plus root 2 alpha. Root 1 plus root 2 plus so on till root n. And this is like approximately n root n. Now you might wonder why. Okay, I'll tell you why. So there are multiple ways of looking at this. So let's take the last root n by 2 terms. It's going to be, I'm just telling you why this is n root n. It might be straightforward to some people, but I'll still explain it because, like, don't take anything for granted. You need to know how everything works, like till the base. N root n by 2 or something like that. Some stuff like that you'll get. Okay. So look, take the last half terms. Like there are n terms here. Take the last n by 2 terms. How will they be? Root of n by 2 plus root of n by 2 plus 1 plus root of n by 2 plus 2, so on till root of n by 2. So on till root of n. There are n by 2 such terms. And each number is at least root of n by 2. Each number is at least n by 2, root of n by 2. So this is going to be at least root of n by 2. And this is some 1 by 2 root 2 into n root n. And we discussed previously, when we are discussing complexities, ignore constants. So it's going to be n root n itself. This whole thing, we know that this is less than or equal to this is less than this. And this, we discussed this at least n by 2 root n by 2. Got it? Yeah. Did everyone understand this? That's how n root n comes. Now, how do we do this quickly? It's n root n. Wait 1 second, just checking. Yeah. So how do we do this like quickly? Like if you want to come, like for each one, if you want to compute it, it's going to take n root n. That might be fine in some cases, but turns out we can do it quickly. How? We do a similar to Sieve method. There's a method that's similar to Sieve, and I'll show it to you. Please comment if there are any doubts. I'm here to explain all of them. So what we do is 1, 2, 3, 4, so on till n. For each number from 1, we mark, initially we have an initial array, empty array, all of them zeros. Like first number is 0, second number is 0, 1, 2. I mean, it starts from, an array starts from 0, I understand that, but this is for interpretation. 0, so on till. Now, we start from 1. We increment all multiples of 1 by 1. 1. It's going to be 1, 1, 1, 1, 1. Now, I'll use numbers instead, it'll be more convenient. 1, 2, 3, 4, 5, 6, 7. All right. Now, we increment all numbers by 1. 1, 1, plus 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 1. Now, we go to 2. We increment all multiples of 2 by 1. Plus 1. Go to 3. All multiples of 3 by 1. 4. All multiples of 4 by 1. 5. All multiples of 5 by 1. There's only one. There's only going to be 1. 6. 1. Now, if you look at the value at each number in the array, for 1 it's going to be 1. For 2 it's 2. 3, 2 factors. 4 there are going to be 3 factors. 1, 2 and 4. This went out flying. 5, 2 factors, plus 1, plus 1. 6, plus 1 from 1, plus 1 from 2, plus 1 from 3, and plus 1 from 6 itself. 7, plus 1 from 1, plus 1 from 7. Fair. Alright. That's it. That's it. The code is also going to be super short and the complexity straightforward. We've discussed all of it. We discussed the complexity also very clearly before. I'll show you how. So, what we did here, initially we initialized the array to 0, and then for all numbers from 1 to n, we incremented its multiples. And then we do this for all numbers from 1 to n. In the end, the array that we get, the ith number in the array, is going to have the number of factors of I, and that's it. That's it. Like with this, we get all factors of 1 to n, counter factors of all numbers from 1 to n in one go. Now again, you might ask, shit, this is like n square. This seems n square. We are marking all multiples of 1, or marking all multiples of 2, 3, 4, and so on. Isn't that costly? Well, not that costly. So we'll show how. Well, let's calculate it precisely. Like for 1, how many numbers are you marking? N. For 2, we are marking n by 2. For 3, we are marking n by 3. 4, we are marking n by 4. And so on, right? So on till n. Now, once we add all of this up, this is like for 1, we are doing n computations. 2, we are doing n by 2 computations, and so on. Once we add all of this up, what do we get? N plus n by 2 plus n by n plus n by 2 plus n by 3 plus so on n by n. Now we discussed that while calculating complexities of primes. We discussed that this is n log n, right? and that's it. So we are getting the factors, the factor count of all numbers from 1 to n in just n log n compared to n root n previously. Isn't that great? Like, and the code is going to be really small, like very small instead. I'll show it to you. We don't need this boring function anymore. We just need this. For int, we are going to do exactly what we discussed. I equals 1, and you're going to iterate till n. I plus plus. For in j equals I, we are going to iterate multiples of I. How do you iterate multiples of I less than n? J less than equal to n. J plus equals I. Simple, very simple. That's it. Count of j plus plus. For each number, you're updating, you're incrementing count of all its multiples less than n. And that's it, done. 2 loops, which might seem O of n square at first. That's simply n log n. And we discussed how, like, you can rewind the video back a bit to discuss the, we discussed the proof as well. Like splitting the number into binary and stuff and adding them. It's going to be n log n. Well, not binary exactly, but you get the gist. Yes, so that's it. That's count of factors. Any doubts so far? Please let me know. All right. Let's solve a problem. Okay, Sumita, judging number theory questions in CF contest is very tough nowadays, but after seeing editorial, it's just implementation. Yeah, Sumita, I understand that. So, like, I plan to do some number theory problems on this channel. Like in the next few videos, I'll try to like take up a few problems and solve them from scratch. So usually number theory problems, like, actually the method depends on the problem itself, but I shall try to do those problems in front of you. Like, I shall try various methods, and I will show you the failed ones, and I'll show you, like, hopefully make it easier for you to solve problems in the future. Yeah, don't worry. Practice is the key. So let's move on to the next problem. Also, let me know if there's any problem you want me to solve, or do comment it in the comment section, like problem link. I'll explain it in the next class. Like, I do look at the comment section after the class, so please let me know. So here's the problem. Given an array of integers a1 to an, find the number of pairs I comma j where ai is a multiple of aj. So find the number of pairs of integers where one is a multiple of the other. Look at the question carefully, read the question carefully. Think for a minute. Meanwhile, I'll explain the question with an example as well. So ai, aj, where find the number of pairs where ai modulo aj equals 0. And one sec. Yeah, simple. And ai is not equal to aj. So if you look at the 2, 3, 2, 3, 4, 5, 2, the answer for this is one pair. This is one pair. Answer for this is 2. And let's look at another example. 2, 3, 6, 8. 2, 6 is one pair. 3, 6 is one pair. 2, 8 is one pair. The answer for this is 3. Cool. Now, For small n, like if n is 5 or 10, you can do it with hand. If n is 1000, you can do it with the computer using brute force. For all pairs, you check if ai is not equal to aj and a is a multiple of aj or aj is a multiple of ai. It's going to be O of n square, doable for n equals 1000 or maybe 5000 or something. Because n square, what is n square if n is 1000 or 5000? It's up to 10 power 6 to 10 power 7, which is okay for a computer. But if n is up to 10 to the power 5, doing the brute force method of checking each pair is going to take 10 to the power 10 operations. But usually in competitions, you might want to be a bit more quicker, like because 10 power 8 is the limit. And doing 10 power 10 would take 100 seconds, which is not desirable. So what we do here, we try to make an observation. That's it. So, yeah. If you have any ideas, please do put it in the live chat. I'll keep putting an eye on it. So what we do here, so 2 comma 3 comma 5 comma 7 5 comma 2 comma 15. Say this is the answer, like this is the input. Now what do we do here? Like we need to do something smart here, like because we can't do the n square thing. What if we had the number of multiples of 2 which are not equal to 2 in the array? Like for this the answer is 0. For 3, number of multiples of 3 which are not 3, it's 15. Just 15. 1 1 0 0. Like if we had this array, wouldn't it be cool? We can just sum this up. We can just sum this array and that's our answer. Number of multiples of 2 which are not 2, number of multiples of 3 which are not 3, so on. Say we had 2 comma 3 comma 7 comma 6 comma 42. Number of multiples of 2 which are not 2, which is 6 and 42, 2. Number of multiples of 3 which are not 3, 6 and 42, 2. Number of multiples of 7 which are not 3, which are not 7, 1. 6 which are not 6, 1. 7 for 42 it's just 0. If we had this array, the answer for this is just 4. Sorry. 2 plus 2 plus 1 plus 1, 6, right? If we had this array, wouldn't it be cool? It would be cool, right? One way is like we have two. One way to compute this array is for each number, see how many numbers are not 2 and are a multiple of 2. And do that for 3, do that for 7, but that would be long and boring. We need to be somewhat lazy here. Again, we use the Sieve method. The Sieve method is very convenient when it comes to divisors of a large range of numbers, or the Sieve method is very convenient when you have to deal with divisors or a lot of number theoretic problems which deals with coprime or GCD. Well, you might not know now, but when you are actually dealing with computing factors of all numbers from 1 to n or multiples of all numbers from 1 to n, something like that, it's good to start thinking with the Sieve method. It's going to, like, it uses the really cool fact that n by 1 plus n by 2 plus n by 3 plus n by n is not n square, it's n log n. It uses that fact, and it can usually make things easy for you. And I've seen that being used in a lot of problems, especially in Codeforce's div to C or div to C or sometimes D. Yeah. So Sumit, you can try to think in that direction sometimes. So it's all about exploring different ideas, and if you don't get it, it's okay. But yeah, it's about exploring the idea. Now, how do we do this question? All right, let's discuss about it. Say you're given the input A, right? Now you want to construct the new array where for each number we saw 2, 3, 6, 7, 42. We want to construct this array 2, 2, 1. Yeah, that's it, right? You want to construct this array and you want to do it quickly. Yeah, you want to do it quickly. So, any ideas in the comment section? How would you do it using the Sieve method? How would you compute this array using the Sieve method? Yeah. All right, I'll show it to you. So one way would be to use the fact that all the numbers are from 1 to 10 to the power 5. 1 less than ai less than equal to 10 to the power 5. What if I told you you could compute this array like for all x from 1 to 10 to the power 5, we compute how many multiples of x which are not x are there in this. That is, for x equals 1, first sort and then apply, Pankaj says. I'm not sure you reached the solution. Can you describe it more? I'll reach to the. I'll try to read that once I describe the solution. X equals 1. All multiples of, we see how many multiples of x which are not x are there in A. How many multiples for x equals 2? How many multiples of 2 other than 2 which are not there in this, which are there in this, and so on. And again, how do we do that? I'll show it to you. So we have the array 2, 3, 6, 7, 42. Let's add a duplicate just to be more like fair. Now let's make another count array where count of 2 equals 2, count of 3 equals 1. Let's add another 42 in the end just for gags. equals 2. All right. Now, for all numbers from 1 to 10 to the power 5, I equals 1 to the 10 to the power 5. Let's mark m of I is equal to number of multiples of I that are not I which are present in this array. And how do we do that? It's by again sieve. We start by we see how many, we see the count of 2i. Well, crap. We see the count of 2i, see the count of 3i. So basically m of I is equal to count of 2i plus count of 3i plus so on. Similarly, m of 1 equals m of count of 2 plus count of 3 plus count of 4 plus so on. M of 2 equals count of 2 plus count of 4 plus so on. M of 3 equals count of 3 plus count of 9, sorry 6, I'm sorry, plus so on, all multiples of 3. But this is wrong. We shouldn't use 2 here. We should start from 4 itself. 4, 6, 8. This shouldn't be there. Count of 4 plus count of 6 plus count of 8. Count of 6 plus count of 9 plus count of 12 for m of 3 and so on. Right? And now, once we have the m array, we can calculate the array that we wanted initially to get the answer. The answer for 2, 2, 2, 2, 3, 6, 7, 42. 42. We add another 42, right? Now turns out I have lack of space. Yeah. Number of multiples of 2 which are not 2 is, this is just m of 2 now. M of 2. This is m of 2. M of 3. And so on. Now we sum it up. We get the answer. That's it. Yep. Let's dry run it on this example. 2, 2, 3, 6, 7, 42, 42. What is m of 2 here? Is equal to count of 4 plus count of 6 plus so on. So count of 4 is 0. Count of 6 is 0. So this is basically count of all even numbers other than 2. That's basically 6 plus 42 plus 42. That's basically 3. M of 2 equals 3. M of 3. Similarly, 1, 1, 2, 3, 3. Count of 3 plus M of 3 is count of 6 plus count of 9 plus so on till, since 42 is a multiple of 3, count of 42 is also included here. 3. Similarly, M of 6 is equal to count of 42. That's it. 1, 2. Because count of 42 is 2. Now, that's it. Let's look at the code first and we'll see how, then we'll come back to the complexity. It'll be more easier that way. Now, first you take the, like, if you had to do it in the, competition, say if it says it's a competition and you have to do it, like, this is how you would write, right? Take in an array, declare a vector of int. You can declare an array as well. This is as good as an array of size n. I'm taking this max n plus 1. It's not required, but still. Taking the input as an array. This is all just input. Alright, this is just input part. Input done. Now we have to calculate count of each element. Got it? So what we use? Vector int. We declare a count array of size max n. Alright, this is up to 1e5, 10 to the power 5. Now for each number, please let me know if you're like losing track or anything. I'll try to explain that part even more clearly. I'm here for that. Alright. Got it. Count of AI plus 1. Now that we have counting finish, now we calculate the M array. M array is the number of multiples which are not equal to I. Number of multiples of 5 which are not equal to I. M max n. I less than or equal to n. Swamalu Gadai says, asks what's meant by CodeChef, CodeVersus and LeetCode. So CodeChef is an online competitive programming platform where you can solve algorithmic problems and so on. CodeVersus is something that explains programming, like it's absolutely for people who are starting with programming and who want to improve in programming, competitive programming in general. And I think LeetCode is something for an interview preparation. It's an interview preparation platform. Do one video explaining these differences. I'll think about it. Max n, I plus plus. For all numbers from 1 to max n, you're updating. You want to calculate how many numbers, how many multiples of I are there, which are not I. You'll understand it. For int j equals 2 into I, not I. Not I, 2 into I. J less than max n, j plus equals I. So what this does is, this iterates over all multiples of I which are not I. 2i, 3i, 4i, not I. Now, m of I plus equals count of j. Now after computing all of this, the M array, the x, for example, the third element of the M array, M of 3 will tell you number of multiples of 3 in the array A which are not equal to A. Got it? Yeah. M array has been computed. Now for int, now you want to calculate the answer, int answer. For int I equals 0, I less, answer can be long, so we don't know. I less than n, I plus plus, answer plus is equal to m of a of I. See out answer. Now what did we do here? This is m of a of I is going to tell you for each number how many numbers are there, how many multiples of this number are there in the array which are not equal to A. That's what the question asked. How many pairs of integers are there, AI, comma AJ, where AI is a multiple of AJ, but AI is not equal to AJ. And we are doing that for each number, and we are summing this over all numbers. Fairly straightforward, nothing complex. Any doubts, please ask. And the complexity of this is, well, I guess I don't need this. Yeah. This is O of n. This is O of n. This, as we discussed, for a given I, it's going to happen only n by I times. N by I times for each I. And for I equals 1, 2, if you sum it all over, we discussed that this is n log n. Sieve type logic, n log n. And this is O of n. So the total complexity is n log n compared to what we had previously, which is n square root of n or whatever that is, or n square actually, which is bad. This is faster. So it's making the observe, like wherever there are divisors or factors, it's usually a good idea to have Sieve in mind to think about approaching the solution. That's it. Yep, Pankaj Kumar, right, your n log n. This is n log n. And it's very easy to understand how to implement it as well. Sumit, you did, okay. Yep. Any doubts in this question? I'll try to solve more questions on this topic if you need it. It's very crucial for solving number theory problems, a lot of number theory problems. But all right. I guess we can, if you have any questions, I'll just wait a minute more. And if you don't, Sumit saying logic building is difficult while solving such questions. I agree, Sumit. Yeah. But honestly, there's no other shortcut other than just practicing more and more problems. You practice 10 problems of this, you're more likely to get the 11th problem. And it's just pure practice. Just try to understand what doing the Sieve gives you. Like, it doesn't come naturally. Like, it's not going to come on the first go. It's not going to come on the second go, not on the fifth go probably. But you just need to keep practicing, be consistent. Like, just try to understand the essence of what Sieve does. It iterates over factors, it iterates over multiples of a number. And when a problem asks you to calculate, if a problem needs you to calculate something related to divisors or prime divisors, or try to build a base on like what this actually means. Like, honestly, there's no shortcut other than practicing more problems on this. If you want, I can do more problems on this topic, like Sieve. But honestly, there's no shortcut, I'm not gonna lie. Yeah. pure practice here. Any more doubts? If you have any more doubts, please add it in the question in the comment section. And if you want me to solve any problem, okay, Raghav is asking, what will be the topic in the next session? I will likely be solving more problems. I will be likely be solving problems on, say, number theory-ish, which don't require a lot of prerequisites, but need you to apply some trick which I've discussed now or something. Got it? Yeah. Please suggest a good math book. I'm not sure I have a good math book to suggest, especially for these kind of problems. But I could probably you could probably study like solve easy problems on code forces based on number theory and then build up from there. So code forces has a stack of number theory or math. You can start solving problems from the easy level. If you find it too easy, skip a level. That's still okay. Yep, Sumit directly suggested that, number theory. Awesome. So thank you all. Like, if you think this is going to be useful to you, I'll be taking more lectures on this. Please do like and comment if there's anything you want me to improve, and don't forget to subscribe because there's more content to be learned in this topic especially. And I'm telling you that if you follow my lectures, you will it's going to build you a way to understand medium to hard concepts in math, medium concepts especially. So that's it. Pankaj asking, is number theory basically on implementation? Well, I mean, you need to arrive on what to implement, right? So you need to get the solution first and then implement it. The implementations are usually not so hard. There might be some edge cases sometimes, but it's usually not so hard. It's usually about arriving at the solution, which is the hardest part in number theory, unlike in data structure problems or something. In number theory, it's usually arriving at the solution, which is the bottleneck to getting the solution. And Sumit, yeah, I will complete the math course. Sorry, I had to take a break because of reasons. Thank you all. Please do subscribe. Don't forget to subscribe to this channel and do drop a like if you think it's useful. Thank you.